Hello and welcome to Uncle Mass Online Academy. Today we have chemistry and we're going to talk about gas laws. This is a continuation of our discussion on gas laws. In the previous class, we talked about the state of matter, the kinetic theory of gases, and we briefly talked about the gas laws. So today, we are going to further our discussion on gas laws. And our expectation is that at the end of this class, you should be able to state different gas laws, derive the mathematical expression of different gas laws, and you should be able to represent different gas laws in their graphical forms and solve calculations involving different gas laws. So these are our expectations in this class. We have three basic gas laws. The gas laws. We have three basic gas laws. We have the Charles law, we have the Boyle's law, and we have pressure law. These basic or three primary gas laws are gotten by the variation of volume, temperature, and pressure. When we are varying volume and temperature, we call it Charles law. Charles law. When we are varying volume and pressure, we call it Boyle's law. Boyle's law. And when we are varying pressure and temperature, we call it pressure law. So we have three variations we are considering in gas laws. One, the variation of volume and temperature. If we are varying pressure and temperature, volume and temperature, we are keeping pressure constant. And when we are varying volume and pressure, we are keeping temperature constant. And when we are varying pressure and temperature, we are keeping volume constant. Now, their statements. Charles law. Charles law. Charles law states that at a given pressure, the volume of any given mass of a gas varies directly with the temperature of the gas. At a constant pressure, the volume of a gas varies directly with the temperature of the gas. So there is a direct relationship between the volume and the temperature of a gas. That is the statement of the Charles law. And we know that in mathematics, we use this sign to represent proportionality or variation. So volume varies directly with temperature. For Charles law, we are driving the mathematical expression for Charles law. Now this means that V, if you want to clear the sign of proportionality, we introduce a quality sign and put a constant is equal to, this is the quality sign, then we put a constant K times by T. Now this means that V is equal to KT. Now if we want to make K the subject of the formula, that is to make K stand alone, then we have to take the T to the other side, and that means that V over T, this is multiplication here. If it is coming to the other side, it becomes division. So V over K over T is equal to K. That means that our constant is equal to volume over temperature. Now, if you have different volume and different temperature, then we can say that V1 over T1 is equal to V2 over T2, and if you have more volume and more temperature, you can also say is equal to V3 over T3 to infinity. But let's leave it to only 2 because most of the equations we are going to encounter are going to have only 2 variations, that is 2 volume and 2 temperature. So this is the Charles law. This is the mathematical expression for Charles law. V1 over T1 is equal to V2 over T2. Now the graphical representation of the Charles law. In Charles law, the volume and temperature are varying. So we have a graphical representation of volume and temperature, volume up and temperature down. Now, if the temperature is in Kelvin, we have 2 basic units for temperature, Kelvin and degrees Celsius. Now, the graph goes like this, starting from the origin, it goes up. But if we are leaving the temperature in degrees Celsius, the graph will look like this, starting from minus 273. The graph will go like this. From this negative side, it has a broken line, but then at the positive side, it has a thick line. This is volume and this is temperature in degrees Celsius. So we have 2 graphs for Charles law when the temperature is represented in Kelvin and when the temperature is represented in degrees Celsius. Now this is the graphical representation of the Charles law. Now let's talk about the Boyle's law. The Boyle's law. Boyle's law talks about the variation of volume and pressure. Variation of volume and pressure. And Boyle's law states that at a constant temperature, the volume of a given mass of a gas is inversely proportional to the pressure of the gas. The variation between volume and pressure is inversely proportional, but the variation of volume and temperature, as we have in Charles law, is directly proportional. Now, if we are having an inverse variation, it means 1 over the value, which means that volume varies indirectly as or inversely to pressure. Now, if you want to clear the sign of proportionality, we introduce a constant and put equality sign. That means that volume is equal to K times by 1 over P. And then our V is equal to K times 1 is K, that is K over P. And now we are going to have that if we want to make the K stand alone, now we take the P to this side. It is division here, so it's going to be multiplication when it comes to the other side. And we are now going to have Vp is equal to K. Now, if you have different volume and different pressure, it means that we are going to have V1 P1 is equal to V2 P2, and it continues like that. So this is the equation for Boyle's law. V1 P1 is equal to V2 P2. The mathematical expression for Boyle's law, V1 P1 is equal to V2 P2. Now the graphical representation of the Boyle's law. The Boyle's law, we are varying volume and pressure. Volume can vary inversely as pressure. In this case, we have a straight line graph passing from the origin up. Then the volume can vary with pressure, not the inverse, with the pressure alone. In this case, we are going to have a graph that looks like this. This means inverse variation. It is coming toward the other side, shifting toward the left. Now we can also have vary pressure and the volume, varying it against the pressure. And in this case, we are going to have a graph that looks like this. This is for the variation of PV over V, PV over P. So these are different forms that we can present the Charles law and the Boyle's law in their graphical ways. For Charles law, we represent it, we have this graph. When the temperature is in degrees Celsius, we have this, and when the temperature is in Kelvin, we have this. Then for Boyle's law, when we are varying the volume with inverse of the pressure, we have a graph passing through the origin, a straight line graph passing through the origin. And when we are varying the volume and the pressure, not the inverse of the pressure, then we have a pressure that looks like this. And when we are varying pressure and volume against the pressure, we have a graph that looks like this. Now we have the pressure law. The pressure law is when we are varying the pressure and temperature, and in this case, the volume is constant. Remember that for Boyle's law, temperature is constant. For Charles law, pressure is constant. And now for pressure law, volume is constant. These are the three basic gas laws. Now the variation of pressure and temperature, the pressure law states that the pressure of a given mass of a gas varies directly with the temperature of the gas at a constant volume. Now when the volume is constant, the pressure of a gas varies directly with the temperature, and this means that P varies directly with temperature. Now if we want to clear the sign of proportionality, we have that P is equal to, introduce a constant K times by T, and so we have that pressure is equal to KT. Now if we want to make K to stand alone, to make K the subject of the formula, we have that P over T is equal to K. Now if you have different pressure and different volumes and different temperature, we are going to have P1 over T1 is equal to P2 over T2. So this is the pressure law. This is the mathematical expression for the pressure law of gas. So we've now driven the mathematical expression for the Charles law, the Boyle's law, and the pressure law. Now we have other equations for gas laws. We can combine the volume, that is the Charles law and Boyle's law, and when we combine two of them, we get an equation that looks like this: P1 V1 over T1 is equal to P2 V2 is equal to P1 V1 over T1 is equal to P2 V2 over T1. This is the general gas equation. General gas equation. In this case, we are given three parameters. If we are given different pressure, volume, and temperature, then we can find the parameter that is missing by using this general gas equation. Now we have another equation which we call the ideal gas equation. The ideal gas equation states that PV is equal to nRT. PV is equal to nRT. This is pressure, the product of pressure and volume is equal to number of mole times by gas constant times by temperature. Here, this is equal to pressure, V is equal to volume, N equals to number of moles, R equals to gas constant, and T is equal to temperature. So these are the 5 different gas law equations: the Charles law, the Boyle's law, the pressure law, the general gas law equation, and the ideal gas law equation. Now this gas law, in this ideal gas law, R is a constant that has the value of R is always R is equal to 0.0821 or 8.31. Now we have different places that we can use this constant. There's a time we can use it as 0.0821 and the time we can use it as 8.31. Now the unit for this one is ATM per dm cube, ATM dm cube per Kelvin per mole. So when the unit is given as this, when the unit of pressure given to us is in ATM, we use this value. Then we have this value also as 8.31 joules per mole per Kelvin. So if the pressure is not given in ATM, then we have to use this R, this value for R, 8.31 joule per mole, or they can tell us exactly which one we are going to use in the calculations. Now please note that anytime you want to solve a calculation involving gas laws, this is very important. Temperature must be in Kelvin. The temperature must be in Kelvin. If you are given any temperature and it is in degrees Celsius or any other form, we must convert it back to Kelvin. The gas laws are valid only when the temperature is given in Kelvin. All of them, the temperature must be in Kelvin. If you leave it with the unit given to you, if it is not in Kelvin, we are not going to get the answer. So this is very, very important, that all the temperature must be converted to Kelvin before you start solving or using them to do your calculations involving gas laws. Now let us solve some examples. All the examples I'm going to solve are from past wire questions. We solve example 1. Example 1. Example 1. In this example, we have that a gas occupies a gas occupies 500 cm cube at 27 degrees Celsius. Full stop. Calculate the volume. Calculate the volume at 40 degrees Celsius at if the pressure is constant. If the pressure is constant. Now solution. Calculate a gas occupies 500 cm cube. The volume, the first volume, 500 cm cube. We call this volume 1 or V1 at temperature of 27 degrees Celsius. This is T1, the first temperature. Then calculate the volume at 40 degrees Celsius. T2 is 40 degrees Celsius, and we are now looking for the volume. Now the pressure is constant. This means that this is a Charles law, and we know that in Charles law, solution. In Charles law, we have V1 over T1 is equal to V2 over T2. This is the mathematical expression for Charles law. Now, what is our V1 and what is our T1? What is our V2 and what is our T2? Our V1 is equal to 500 cm cube. Our T1 is equal to 27 degrees Celsius. Now, our V2, we are looking for it, is unknown, and our T2 is equal to 40 degrees Celsius. Now, the first thing to do is now to convert the temperatures from degrees Celsius to Kelvin. Converting the temperature, T1, which is equal to 27 degrees Celsius, becomes, to convert degrees Celsius to Kelvin, we add 273 to it. If we are given any value in degrees Celsius and we are asked to convert it to Kelvin, what we do is that we add 273 to the value and then we get the value in Kelvin. So for 27 degrees Celsius, to convert it to Kelvin, we add plus 273. Now whatever it gives us is now the temperature in Kelvin. So T1 is equal to 27 plus 273, and this gives us 300 Kelvin. Now the T2 is also in degrees Celsius, so we have to convert it 40 degrees. To convert it to Kelvin, we add 273 again, and when we add it, now we have that our T2 is equal to 40 plus 273. This will give us 313 Kelvin. Now we have that our T1 is equal to 300 and our T2 is equal to 313. Then our first volume is 500 cm cube. Then we are looking for the second volume. Now if we put everything in the Charles law, then we are going to have that V1 over T1 is equal to V2 over T2. This becomes V1 is 500. This becomes 500 over T1 is 300 as calculated. is equal to V2, which is what we are looking for, over T2 is 313. Now we make V2 the subject of the formula. So we are going to have that if we want to make it the subject of the formula, then we take this one to this side, leaving only the V2. If you are taking it to this side, it is division here. If it is coming to this side, it becomes multiplication. And so we have that V2 is equal to 500 over 300 multiplied by 313 multiplied by 313, and this will give us that V2 is equal to 500 multiplied by 313 everything over 300. Now this will give us that our V2 is equal to, if we divide this, we are going to get 521.7 cm cube. This is the answer. 500 times 313 over 300, it will give us 521. Now this question is from WAEC theory question 1995, question number 4II. Question number 4II. This is WAEC 1995, question number 4II. So you can look for it and see how it is being solved. So this is our example 1. Then example 2. Example 2, we can have a variation of, okay, let's have this example 2. This example 2 is from WAEC question. Example 2 is from WAEC question, WAEC 2011, question number 1. WAEC 2011, theory question number 1. Now the question is this: the table below gives the volume and pressure data for a particular sample of a gas, at a given temperature. Now the table is this: we have volume and we have pressure. Now we have 4.00, and then we have 1.00, then we have 2.00, and we have 2.00, and now we have 1.00, and we have 4.00. Now this is the table. Now the question is now calculate the pressure of the gas when the volume is 3.2 3.20 dm cube. 3.20 dm cube. Now, how do we solve this? Solution. Now, what we have in the table is a data of volume and pressure. When we are varying volume and pressure, this is Boyle's law. In Boyle's law, we have the volume and the pressure varying, and the Boyle's law states that the mathematical expression for Boyle's law is that V1 P1 is equal to V2 P2. Now, what is our P1? What is our V1? And what is our P1? What is our V2? And what is our P2? We are asked to calculate the pressure when the volume is 3.21. Now here, we can find V1. V1, what we can do is that you can just come to the table, pick any particular volume, any particular column, look for the pressure there and the volume that is there. So V1, let's pick the first column, the first one. So volume is 4 and pressure is 1. So this becomes our V1 and this becomes our V2, our P1. This is V1 and this is our P1. Now we are looking for P2 when volume is 3.20. We can pick any of these, but if we pick from here, we must pick the one under it. So if we pick 2.00, we also have to pick 2.00 here. If we pick 1.0, we have to pick 4.0 here. We decided to pick the first one, which is 4.00 and 1.00. So we are going to have that V1 is equal to 4.00. Our P1 is equal to 1.00. Now we are given second volume as 3.20, and we are asked to find the value of P2. P2 is what is unknown. There is nothing to convert. We are not given temperature here, so we are not converting. So we use the values directly. Now we put these values into the Boyle's law, and we are going to have that V1 T1 is equal to V2 T2. This becomes V1 is 400, not 400, 4.00, which is 4, over T1 is 1, that is 1.001. Now this is equal to, we are looking for, we have V2 as 3.20 over T2, we are looking for it, T2. Now if you make T2 the subject of the formula, or we do cross multiplication, T2 times by 4 is equal to 1 times by 3.2. 4 times T2 is equal to 1 times 3.20. Now this means that 4T2 is equal to 1 times 3.20 is equal to 3.20 is equal to 3.20, and our T2 is equal to 3.20 over 4. Now this means that our T2 is equal to, it's not T2, P2. We are solving with Boyle's law. We are solving with Boyle's law and not Charles' law. V1 P1 is equal to V2 P2. So what we are going to have is from V1 P1 is equal to V2 P2. Now we have that 4 times 1 is equal to V2 is 3.20 times by P2, and then 4 times 1 is 4 is equal to 4 times 1 is 2 is 4 times 1 is 4 is equal to 3.20 P2. And now we are going to have that P2 is equal to 4 over 3.20, which means that P2 is equal to 1.25 ATM. This is the answer. Now we solve another example. We have solved the one involving Charles law, the one involving Boyle's law. Now let's try to look for the one that involves pressure law. That is where we have the temperature and the pressure varying. So let's see if we can see something like temperature and pressure. Okay, now if we have that okay, we have example 3. If the temperature of a gas is 273 at STP, calculate the pressure of the gas. Calculate the pressure of the gas calculate the pressure of the gas when the temperature is 204 Kelvin. Now take the pressure of a gas pressure at STP. STP is equal to 1 ATM. Pressure of a gas is equal to 1.01 times by 10 raised to power 3 Newton per meter squared. Now here, solution. For here, we have that if the temperature of a gas is 273 Kelvin at STP, calculate the pressure of the gas when the temperature is when the temperature is 204 Kelvin, and it is given to us that at STP pressure is equal to 1.01 times by 10 raised to power 3 Kelvin, 10 times by 10 raised to power 3 Newton per meter squared. Now here, T1 is equal to 273, that is at STP. Now we are given that at that STP, pressure is equal to 1.01 times by 10 raised to power 3. This is our P1. Now we are given T2, and we are asked, T2 is 204 Kelvin, and we are asked to look for P2. Now this is a variation of volume, a variation of temperature and pressure. And when we are varying temperature and pressure, this is called the pressure law. Pressure law is the variation of temperature and pressure, and the equation is P1 over T1 is equal to P2 over T2. Now we have our P1 and we have our P2. We have our P1, we have our T1. We don't know our P2, but we know our T2. So we put everything and look for the unknown. P1 is 1.01 times by 10 raised to power 3 over temperature is 273, that is T1. Now everything is equal to P2 is what we are looking for, and T1 and T2 is 204. Now we make P2 the subject of the formula. P2 now, standing alone, becomes, or we just do cross multiplication to make everything simpler for us. We cross this by this. That means P2 times 273 is equal to 1.01 times by 10 raised to power 3 times by 204. P2 times 273 is equal to 1.01 times by 10 raised to power 3, then times by 204. And this means that if we want to make P stand alone, then P2 is equal to this side divided by 273, which is 1.01 times by 10 raised to power 3 times by 204 over 273. And whatever it gives us is the answer. Now note that here we did not convert anything because the temperature given to us is already in Kelvin. If the temperature is already in Kelvin, there is no need for conversion. But if the temperature is not in Kelvin, we must convert it to Kelvin before we use it to do the calculation that we want. Now we solve another example. Let's solve example that involves general gas equation. Now this is from WAEC 1992, question number 16, OBJ. The question is, if the volume, if the volume of a gas of a given, if the volume of a given mass of gas at 298 Kelvin and pressure of 205.2 times by 10 raised to power 3 Newton per meter squared is 2.12 dm cube. What is the volume? What is the volume? The volume of the gas. What is the volume of the gas? At STP. Now we are given that at STP pressure is equal to 101.3 times by 10 raised to power 3 times by 10 raised to power 3 Newton per meter squared. Now here, the parameters given to us, T1 is equal to 298. If the volume of a given mass of a gas at 298 Kelvin, the temperature is already in Kelvin, so there's no need of converting this temperature again, and pressure of 205.2 times by 10 raised to power 3 Newton per meter squared is 2.12 dm cube. This is the volume. And what is the volume of the gas at STP? Now the first temperature given to us is 298 Kelvin, no need of conversion. Now P1 given to us is 205.2 times by 10 raised to power 3 Newton per meter squared. Now the first volume given to us, V1, is equal to 2.12 dm cube. And then they said at STP temperature is equal to 273 and pressure given to us is 101.3 times by 10 raised to power 3. So at STP, then that becomes our temperature for T2, that is equal to 273, and our pressure P is equal to, P2 is equal to 101.3 times by 10 raised to power 3. So we use this to solve. If the volume of a given mass of a gas at 298 Kelvin, this is T1, the first T, now, and pressure of 205.2 times by 10 raised to power 3, this is the first pressure, P1, is 2.12 dm cube. This is the first volume, V1. Now, what is the volume of the gas at STP? At STP, temperature is equal to 273 Kelvin. That is our T2 now. And pressure given to us now is 101.3 times by 10 raised to power 3 This is our P2. Now we put everything into the general gas equation. The general gas equation states that P1 V1 over T1 is equal to P2 V2 over T2. Now if we put everything into the equation, we are now going to have that, or first of all, let's make the one we are looking for the subject or the formula from this. We are looking for P. What is the volume? We are looking for V2. So we make it the subject of or the formula. Now we transfer this to this side and now divide everything by P2. So we are going to have that V2 is equal to P1 V1 over T1 multiplied by T2 then divided by P2. So this is going to give us P1 V1 times by T2, then everything over T1 P2. Now this is equal to V2. Now we are going to have, if we put everything, P1 is 205.2 times by 10 raised to power 3. V1 is times by 2.12, then times by T2 is 273, then this everything over T1 is 298, then times by P2 is 101.3 times by 10 raised to power 3 times 101.3 times by 10 raised to power 3. Now if we multiply this, we are going to have that V2 is equal to 1187,61552 everything over 301,87400, and if we divide this, we are going to get that our V2 is equal to 3.934 dm cube. This is our answer. Now let's try to solve ideal gas equation. Now if we have example 5, what is the amount in mole of a sample of gas which occupies 5 dm cube at 3 atm and 15 degrees Celsius. Now we are given that gas constant R is equal to 0.082 atm per dm cube, dm cube per Kelvin, atm cube per Kelvin per mole. Now to solve this, solution for ideal gas, when we are given R, we begin to suspect ideal gas law. And for ideal gas, PV is equal to nRT. Can we get our P? Can we get our V? Can we get our R and T? We are looking for the number of mole, and number of mole is the small n. Now, P given to us, what is the amount in mole of a sample of gas which occupies 5 dm cube? This is the volume given to us at pressure of at 3 atm. Pressure is measured in atm. This is one of the units for measuring pressure. So when we see atm, we know that we are talking about pressure. So the pressure given to us is 3 atm and volume is 5. Then and temperature is 15 degrees Celsius. Then we have the gas constant. Now the first thing for us to do is to convert the temperature given to us to Kelvin before we use it to solve. So we have that temperature, which is equal to 15 degrees Celsius, must be converted to Kelvin. The way to convert it to Kelvin is to add 273 to it. So we say 15 plus 273. This gives us 288. Now we use the temperature 288 to solve, and that means that PV is equal to nRT becomes P is 3 atm, times by volume is 5, is equal to, we are looking for N, times by gas constant given to us is 0.082, times by temperature is 288. Now with this, we can say that N is equal to 3 times by 5, everything over 0.082 times by 288, and this gives us that the value of N is equal to 0.64 moles. So this is the answer to this question. So here in this class, we have discussed the different gas laws, and we're able to derive the mathematical expression for each of the different gas laws, and then we stated the different equations, different gas law equations, and then we have also given the graphical representations of different gas equations, and then we solved some examples involving gas equations or gas laws. So this is